In this lesson, we are going to continue discussing how to determine whether series converge using direct comparison tests and limit comparison tests, and also summarize all of the tests we have learned so far. So first, let's just review what the direct comparison test says. Suppose you have two series, A sub n and B sub n, where the series have positive terms. And one important thing is math is before you apply a test, you have to make sure that your conditions are, your hypotheses are satisfied. So if your series does not have positive terms, you cannot use a direct comparison test. And we suppose that A sub n is bigger than 0, but less than or equal to B sub n for all n. Now the first part of the comparison test says that if the series of B sub n's converge, then so does A sub n's. And you can think about it in the fact that B sub n is above A sub n, and so if the larger series converges, the smaller one has to also. So if the larger converges, so does the smaller. And similarly, if the smaller one diverges, so if A sub n diverges, B sub n's terms are all greater than A sub n's, so B sub n has to diverge as well. So if the smaller series diverges, then the larger one diverges also. So that was the direct comparison test. Also, we had the limit comparison test. So how you can apply this is you have two series with positive terms, and if you find the limit of the A sub n's over the B sub n's, and this is equal to some value c, and c is a finite number where c is bigger than 0, either both series converge or both diverge. And usually A sub n is the series that you're given that you're testing, and you find some series which you know converges or diverges to compare it with. And thus far the two series you kind of know a lot about are P series and geometric series. So let's determine whether this series converges or diverges. So when you're using a test, make sure you tell me which test you're using. I'm going to use the limit comparison test, and I'm going to let A sub n be n cubed over n to the 4th minus 1. So that's the terms of the series that I'm given. And B sub n, I'll take the sort of most important terms from the numerator and denominator. So n cubed over n 4th will be 1 over n. And I know that the sum of the B sub n's diverge. So now let's find the limit as n goes to infinity of A sub n over B sub n. So that's the limit as n goes to infinity of n cubed over n to the 4th minus 1 over 1 over n, or multiplied by n over 1. So the limit as n goes to infinity of n to the 4th over n to the 4th minus 1. So dividing the numerator and denominator by n to the 4th, we get 1 over 1 minus 1 over n to the 4th, and that limit is equal to 1. So thus, by the limit comparison test, you know that the sum from n equals 2 to infinity of n cubed over n to the 4th minus 1 diverges. Next, let's determine whether the sum from n equals 1 to infinity of 1 plus 4 to the n over 1 plus 3 to the n converges or diverges. So if only those 1's weren't in the numerator and denominator, we would have a geometric series with r equal to 4/3. So we're going to again apply the limit comparison test. I'm going to let my A sub n equal 1 plus 4 to the n over 1 plus 3 to the n, and the B sub n's equal 4 to the n over 3 to the n. And we know that the sum from n equals 1 to infinity of the b sub n's diverge because it's a geometric series with r equal to 4/3. So if this limit is equal to some finite number, we'll know that our series also diverges. So let's find the limit as n goes to infinity of a sub n over b sub n. So that will be the limit as n goes to infinity of 1 plus 4 to the n over 1 plus 3 to the n multiplied by 3 to the n over 4 to the n. You divide by b to the n, that reciprocates the b to the n. So distributing that through, we have the limit as n goes to infinity of 3 to the n. 3 to the n times 4 to the n will be 12 to the n over 4 to the n plus 12 to the n. Now, multiplying the numerator and denominator by 1 over 12 to the n, that will give us the limit as n goes to infinity of 1 over 4 to the n plus 1 over 1 over 3 to the n plus 1. And as n goes to infinity, 4 to the n goes to infinity, so 1 over 4 to the n goes to 0. 1 over 3 to the n goes to 0. This limit will equal 1. So by the limit comparison test, the series from n equals 1 to infinity, 1 plus 4 to the n over 1 plus 3 to the n, is also going to diverge. Next, let's determine whether the series from 3 to infinity of n plus 2 over n plus 1, the quantity cubed, converges or diverges. So the first thing that I would suggest is determining what n plus 1 cubed is equal to. So just note that n plus 1 cubed is not equal to n cubed plus 1. Think back to the basic definition of exponentiation. N plus 1 cubed means n plus 1 multiplied by n plus 1 by n plus 1. I mean, that's just algebra 2. When you multiply that out, here's what you should get. Well, if n plus 2 over n cubed plus 3n squared plus 3n plus 1. Alright, so I'm going to let a sub n equal n plus 2 over n cubed plus 3n squared plus 3n plus 1. And then the b sub n's, looking at the most important part of the numerator is n, and the denominator is n cubed. N over n cubed will be 1 over n squared. So the b sub n's are 1 over n squared. And we know that the sum from n equals 3 to infinity of 1 over n squared converges because it's a p series with p equal to 2. So let's find a limit as n goes to infinity of the a sub n's over the b sub n's. So that will be n plus 2 over n cubed plus 3n squared plus 3n plus 1 multiplied by n squared over 1. So that'll give us n cubed plus 2n squared over n cubed plus 3n squared plus 3n plus 1. And dividing the numerator and denominator by n cubed, we'll have 1 plus 2 over n over 1 plus 3 over n plus 3 over n squared plus 1 over n cubed. And that limit is equal to 1. And so then, by the limit comparison test, the sum from n equals 3 to infinity of n plus 2 over n plus 1 cubed is going to converge. Lastly, let's determine whether the sum from n equals 1 to infinity of n plus 1 over n root n converges. So let's let a sub n equal n plus 1 over n root n, and b sub n, the most important or dominant power in the numerator, or dominant term, is the n. The denominator is n root n. So b sub n will let equal 1 over root n. And we know that the sum from n equals 1 to infinity 1 over root n diverges. So now let's find the limit as n goes to infinity of a sub n over b sub n. So that will equal the limit as n goes to infinity of n plus 1 over n root n multiplied by root n over 1. So of n root n plus root n over n root n. So if we divide the top numerator and denominator by n root n, the limit as n goes to infinity of 1 plus 1 over n over 1, which is once again 1. And so since this limit is a positive finite number, by the limit comparison test, the sum from n equals 1 to infinity n plus 1 over n root n diverges. The last thing we're going to do in this lesson is review all of the tests that you have learned about series thus far and have a bunch of mixed up examples where you have to choose which one to apply. So the first one is the nth term test. So suppose you're given a series, sum from a sub n. So what the nth term test says, or the test for divergence, is that if the limit as n goes to infinity of the terms is not equal to 0, the series diverges. It doesn't mean that if the limit goes to 0, the series converges. It just will tell you that it's going to diverge no matter what. Next we have geometric series. So a geometric series is one of the form, a sum from n equals 0 to infinity of a times r to the n. And that's equal to a over 1 minus r, so long as the absolute value of r is in between 0 and 1. Otherwise, this series will diverge. Next, we had the p-series test. So this is a series of the form sum from n equals 1 to infinity 1 over n to the p. This will converge if p is greater than 1, and it will diverge if p is between 0 or equal to 1. Now, telescoping series are series of a form where certain terms start to cancel each other out. So it might be something like a1 minus a2. The next term would be an a2 minus a3, etc. And you have successive terms, or sometimes semi-skipping terms, canceling each other out. In the case of the telescoping series and the geometric series, you can actually figure out what the sum is. Next we have the integral test. So you had to have a function f that is continuous, positive, and decreasing. If those three conditions are not met, you cannot apply the integral test. And what the integral test tells you is that the sum from n equals 1 to infinity of a sub n, that will converge if the integral from 1 to infinity of f of x dx converges. And also this will diverge if the integral diverges. Now finally, both the direct comparison test and the limit comparison test suppose that you have series, so a sub n and b sub n with positive terms. And if we have that 0 is less than a sub n, which is less than or equal to b sub n, you know two things. If the b sub n converges, so does the a sub n, and also if the a sub n diverges, so does the b sub n. And then lastly, the limit comparison test, which we were just using, says that if the limit as n goes to infinity of a sub n over b sub n is equal to some c, where c is bigger than 0, then a sub n and b sub n either both diverge or both converge. So determine whether the following series converge or diverge and identify which test was used. So for this first example, what you should notice is that the exponents can subtract here and cancel out a little bit. So we have, this is the same thing as the sum from n equals 1 to infinity of 1 over n to the 9/2 power. You can get that by noticing that root n over n5 is n to the 1/2 over n to the 5th. So that's n to the 1/2 minus 5, which will be negative 9/2, giving you 1 over n to the 9/2. And this converges, and then give me a reason. And the reason is a p series with p equal to 9/2, which is greater than 1. So that's why that series converges. Next, I have the sum from n equals 1 to infinity of 5 times negative 2/7 to the end. This series is going to converge. It's a geometric series with r equal to negative 2/7. Now, in order to figure out what this actually converges to and to use our formula, we have to change the index. So instead of beginning at 1, we have to begin at 0 and change that to negative 2 over 7 to the n plus first power. And then we're going to peel off a negative 2/7. Multiplying it by that 5 gives us negative 10/7 times negative 2/7 to the n power. And thus this sum, remember the formula is a over 1 minus r, will equal negative 10/7 divided by 1 minus negative 2/7. So we have negative 10/7 divided by 9/7, which will be negative 10/9. Next, we have the sum from n equals 1 to infinity of 5n over 2n plus 9. And notice, if you find the limit as n goes to infinity of 5n over 2n plus 9, that's equal to the limit as n goes to infinity of 5 over 2 plus 9 over n, which is 5/2. And since the terms don't limit to 0, the series diverges by the test for divergence, which is sometimes also called the Nth Term Test. Next, let's determine if the sum from n equals 1 to infinity of 1 over the quantity 5 to the n plus 1 converges or diverges. On this, you have options. You can either use limit comparison or direct comparison. Direct comparison is not very hard, so let's do that. So direct comparison. So first notice that 5 to the n plus 1 is greater than 5 to the n. And thus, if I reciprocate, 1 over 5 to the n plus 1 is less than 1 over 5 to the n. And because 5 to the n is positive, this is also bigger than 0. And as the sum from n equals 1 to infinity of 1 over 5 to the n converges, because it's a geometric series with r equal to 1/5, and 1 over the quantity 5 to the n plus 1 is less than 1 over 5 to the n, the sum from n equals 1 to infinity 1 over 5 to the n plus 1 also converges by direct comparison. Since our previous example used direct comparison, on the next one let's use a limit comparison test. So first of all, I'm going to expand out the denominator and write that as n over n to the 4th plus 2n squared plus 1. So we'll apply the limit comparison test with a sub n equal to the terms of the series, so n over n to the 4th plus 2n squared plus 1, and b sub n equal 1 over n cubed. And let's find the limit as n goes to infinity of a sub n over b sub n. That will be the limit as n goes to infinity of n over n to the 4th plus 2n squared plus 1 multiplied by n cubed over 1, n to the 4th over n to the 4th plus 2n squared plus 1. Dividing the numerator and denominator by n to the 4th gives us the limit as n goes to infinity of 1 over 1 plus 2 over n plus 1 over n to the 4th, which will equal 1. And as the sum of 1 over n cubed converges, the sum from n equals 1 to infinity of n over n squared plus 1 squared also converges. Just for reference that we use the limit comparison test. Now the next example, we seem to possibly be having some kind of telescoping thing going on. So let's get an expression for the nth partial sum, s sub n. So when you plug in 1, the first term will be 1/2 minus 1/3 plus. Next plug in 2 and we'll get 1/3 minus 1/4. And then plug in 3 and we'll get 1/4 minus 1/5, etc. Up until our last term where we get 1 over n plus 1 minus 1 over n plus 2. And you're seeing that these terms cancel, the quarters cancel, everybody cancels except for the first thing and the last thing. So an expression for our partial sum s sub n is given by 1/2 minus 1 over the quantity n plus 2. And the value of that sum is given by a limit as n goes to infinity of s sub n. So we have the limit as n goes to infinity of 1/2 minus 1 over the quantity n plus 2, which equals 1/2. And so this series converges to 1/2. So we actually know that that stuff sums up to 1/2. And it is a telescoping series. And the final example is to determine whether this series converges or diverges. So technically you can do this lots of ways. You could use a limit comparison test, you could use a comparison test. This also happens to be a telescoping series, so let's do that one because we can actually find the exact sum. So the first thing we have to do is use partial fractions to break up the 3 over n times n plus 3. So let's do that here. 3 over n times n plus 3 will equal sum a over n plus sum b over n plus 3. Then multiply both sides by n times n plus 3, and we'll have 3 equals a times n plus 3 plus b n. So 3 will equal n times a plus b plus 3a. So we know that 3a has to equal 3, and thus a is 1. We also know, because there's no n on the left side, that a plus b has to equal 0, and since a is 1, b is going to have to be negative 1. So using that information, we can express the sum from n equals 1 to infinity of 3 over n times n plus 3 as a sum from n equals 1 to infinity of 1 over n minus 1 over n plus 3. So let's find an expression for s sub n. So s sub n, when we plug in 1, the first thing we're going to get is 1 minus a quarter. And the next term we'll get will be a half minus a fifth. And the third term we'll get a third minus a sixth. And the fourth term we're going to get a quarter minus a seventh. And it's a lot more than we've listed out in the past, but the reason I do that is terms don't cancel immediately. You see that this quarter is canceling with that 1/4. And eventually the 1/5 will cancel, the 1/6 will cancel, but the 1 stays, the half stays, and the third stays. So we have 3 terms that stay in the beginning. That means that 3 terms are going to stay on the end also. So the very, 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 very last term will be 1 over n minus 1 over n plus 3. The term before that will be 1 over n plus 2 and 1 over n minus 1. And the term before that will be 1 over n plus 1, and then a 1 over n minus 2. And this term, and this term will not cancel, but the other ones will. So the nth partial sum is given by 1 plus a half plus a third minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3. And it is the case that the number of things that don't cancel in the beginning is the same as the number of things that don't cancel on the end. And now if we find the limit as n goes to infinity of s sub n, we'll get 1 plus a half plus a third, because all of those terms go to 0 as n goes to infinity. And a half plus 1 plus 1/3 will be 6 over 6 plus 3 over 6 plus 2 over 6, which is 11/6. So if you were actually asked to find the sum, that is how you would do it, but just to determine whether this converges or diverges, you could have also used some other test to do so.